All right, starting fresh. Sorry, that was not meant to spy. If for some reason you said something you don't want me to hear, don't worry about it. I'm not gonna hold it against you, and I probably won't even hear it, because I'll end up just deleting that. All right, so suppose I want to hit the door with this rubber stopper, and I just swing it around my head. The question is, at what point do I let go? Or potentially, probably not, but potentially a little bit more flexible. I want to hit this spot right there. And I come out here and I start swinging it. At what point do I let go of it so that it will hit?
While it's swinging toward the board.
At what point?
While it's swinging toward the board.
Which means what? All right, so I brought these in markers for a reason. I should use them. So let's set up a incredibly scaled drawing of what we're doing here. And the X is somewhere around there, and I'm swinging this around like this. I'm swinging it, I guess, from an overhead point of view, counterclockwise. Just in terms of language, if I release it at 12 o'clock, I'm releasing it here, 3 o'clock, 6 o'clock, 9 o'clock, and so forth. So what are you suggesting, Musa?
That you release it at around 3 o'clock.
Around 3 o'clock? Any other suggestions?
Yeah, like four or five.
I would say 6.
All right, so here, and then 4 or 5 is at 4:30?
Like between 4 and 5 somewhere, yeah.
2. If you watch the video lesson on this, the one where it's actually in front of a class, you've heard the story before, but I just want to say I did not hit Scott. When I was doing this with the middle school group, I got closer to Scott than I intended, but I did not hit Scott. Scott was prone to exaggeration. But that was first period. Fourth period comes around, and a student walks in and says, "Dr. Fox, I heard you hit Scott this morning." No, I did not hit Scott. Because I was swinging this thing around and I released it, and so in terms of movement, let's see, if we do 6 o'clock, if you two could just sort of move back just a little bit. If there's a certain amount of, I have to swing it, I'd like to swing it fast, but I lose some control. I would suggest moving that way. So we'll do 6 o'clock first. 3. Probably safe, but I think you were okay before. 3, 2, 1. All right, did not come anywhere close to the X. As we start creeping our way around. So that was 6, so 5 o'clock. 3, 2, 1. And I'm hoping at this point you have a sense about where I actually need to release it. It's going to be a great visual for the people watching. Right, so that's somewhere around, so that's somewhere around there. 3, 2, 1. Let's see if we can just cut to the chase here. So the question is 3 o'clock or 2 o'clock. Now we're going to get into some coordination issues. So 3 o'clock is that way, 2 o'clock is there. So somewhere in this region right here is probably the accurate one. But we'll see what 3 does. I released a little bit too early on that one, but I'm hoping that you can see that it went relatively in a straight line. So if I release it here, it's gonna go that way. If I release it here, it's gonna go that way. So somewhere in there, you may return to your seats. The danger is past. And I didn't see what happened to it.
That's right.
Oh, there it is. Okay. Thank you. Why? Why did it go basically in the direction that it was moving at that moment?
Inertia.
Because once you release, when it's moving, you holding it and carrying tension, once you let go, all the momentum that you built up propels it forward from wherever point you let it go.
All right, if we want to use the word momentum at this point. Riley?
You're the epicenter of the forces when you're holding it, but when you let go, it just keeps going forward because it has no epicenter.
Doesn't keep going forward. What do you mean by that?
Straight, I guess.
It does not keep going? Sorry, you're saying it does not keep going straight when I let go?
I said it would then keep going straight because now it has no epicenter.
Why would it have an epicenter?
Because you were holding it when it
Well, let's get technical for just a second. Let's pick at that. I was not touching the rubber stopper. What was causing it? What was causing it to come towards the epicenter?
Strength.
What force?
Centrifugal.
All right. And in this particular case, tension happened to be the,
Centripetal force?
yes, there we go. What's Newton's first law of motion?
Inertia.
I think Newton usually uses a few more words than one. Riley, what-
An object of motion stays in motion unless otherwise acted upon.
so once I let go, what forces are acting on it?
Gravity.
Yeah, I'm gonna pick on that too. Somebody wanna reword that?
The force of gravity.
Okay, I'm good with that. All right, so weight also works there. So once I let go, the only force acting on it is the weight, which acts in which direction?
Downward.
So there are no forces acting in this direction, so there's no reason for it to move in that direction. It will continue doing what it always does. Inertia, basically, whatever it's doing, it's gonna keep doing. In one of the videos, did I talk about Inertia Girl?
Yes.
I did? Okay.
Talk about was funny.
I think I also did state that I did get my daughter's permission to use that story. Except when she took the course. All right, so objects want to move in a straight line. They want to keep doing whatever they're doing. This was a huge departure from basically what was considered to be cutting edge thought for 2,000 years, where things wanted to move into their natural place. But instead, the idea is that things will just keep doing whatever they're doing unless something causes it to act differently. Same is true with circular motion. So if I have an object that's traveling in a circle-ish, there has to be something holding it in because the object wants to move in that direction. So if you're going around a curve, you're not being thrown outwards. What your body does is your body wants to go straight and the car is moving that way. So, paraphrasing and distorting a line from Godfather 3, every time you want to go in a straight line, something just keeps pulling you back in. Now that force is directed towards the center of the circle, and this is where some students mess up in the fact that they miss what the direction of the circle is. Now, obviously I draw a circle like that, it seems clear it's pointing this way. But suppose it's a tilted track. As my attempt at a tilted track, why don't I just do a cross section here? Or just one little piece of it. It's a car going around whatever that is. I have some track tilted at some angle theta. This car is going around in a circle. Where is the center? In which direction is the center of the circle from the car's point of view?
Down.
Huh. Wasn't expecting that one.
To the right?
All right, so we got to the right now. What,
the
explain
right
what
and
you're
down.
thinking with the down.
I was just like to the right and down.
So,
Yeah.
down the ramp.
Yeah.
All right, if that's the center of the circle, that means the car is doing this, as opposed to this.
Okay.
So, Sarah, what's the direction?
Right.
You're right.
That's the direction of the center. So when you go through the facades method, the direction of acceleration is towards the center of the circle. It is not down the ramp. This is not box on ramp. This is object going in a circle. So let's run through a problem. Why don't we start out with a simple case of stopper on string, and we will start out with a nice ideal case of we're doing this in a gravity-free situation. Technically, not that that's really possible, but we can do enough simulations where we can pretend it is. So I have a stopper spinning around in a circle. From here to the center of mass, why don't we, 3 meters. And let's say it goes around 7 seconds to go around in the circle. So, and the reason I'm not using capital T for tension is because capital T stands for period. For things that are repetitive motion, period is how long it takes to do it once. So this is the time for one cycle of repetitive motion. And that is an S, not a 5. Make it look more like an S. Wow, it's even less. And let's give this a mass of 4 kilograms. Not necessarily a realistic problem. Slinging a 4 kilogram mass at the end of a 3 meter string around in 7 seconds is not probably particularly easy. Except it's a gravity-free situation, so we're not dealing with that hassle. All right, so the question is, what is the tension in the string? Let's go through the steps. Some of you might have already have a shortcut, some of you might have, can do this right now, but let's still go through the steps. So force diagram, what are the forces acting on the stopper? Or the 4 kilogram mass?
Force of gravity. Ideal case with no.
Tension's acting on it?
Yes, which way is tension acting on it?
Toward the center of the surface.
So we have tension acting this way. If we wanted to do the full thing, there's a string right here with the tension acting out. If it's an ideal string, there's a tension acting here, and then there's tension pulling on whatever's in the middle of the circle. But this is the part that I really care about. If we go through FTOM, no gravitational force, we have tension. No other, I didn't mention anything else. Normal force, it's not pressing into anything. And friction, if you want to bring in air resistance, knock yourself out. I'm not doing it here. All right. the direction of acceleration.
Is it going clockwise?
It is, oh, you're saying the acceleration going clockwise?
Yeah.
It is not. No. All right, so in terms of left, this thing is traveling in a circle. Obviously, we're doing a snapshot here because the tension is pointing that way. But Newton's second law, what does that tell us?
Force equals mass times acceleration.
Yeah.
Acceleration.
I have only two vectors in this on opposite sides of the equal sign. That has a direction, this has a direction. The directions have to be the same, otherwise, mathematically, this can't work. So the direction of acceleration has to be the direction of the force. So which way, at this moment in time, which way is the acceleration?
Left.
Yep. It is towards the center of the circle. Even if we had more than one force, then acceleration is towards the center of the circle. All right, so that is done those. When I set up my coordinate system, strongly recommend one of your axes is in the direction of acceleration. That's the purpose of the first A. I make that I hat. There's nothing in the vertical direction, so there really is no need for a J hat, but stick one in if you like. Decomposition. Do I need to break this vector up? I got at least 3 people shaking their head no, so let's go with that. The equation of motion. Again, we're using F equals ma as our template. Well, I have only one force, so that's simple enough. It's in the positive I hat direction, so tension is equal to mass times. And then a little bit different from chapters 4 and 5 is the fact that there's a subscript there. Because this is centripetal acceleration. And what does centripetal mean?
Center seeking?
Yes. The center, and then what other word do we have that has PET as the root, meaning pretty much the same thing?
Compete.
That's one of them.
What'd you say?
Compete.
Two groups coming together, seeking each other out. So now we are left with a formula. We have our equation of motion done. We've done that. Substitution. So now, do we have any independent formula for any of these things? The answer is yes. Do we have an independent formula for tension? Like we do for weight or for friction?
Wait, can you repeat that?
When we get to the substitution, the first S here for substitution, the question is, do we have an independent formula for any of these variables? So if weight were in this, we have a formula for weight. Weight is equal to mass times acceleration due to gravity. W equals mg. Friction, we have an independent formula for friction, which has nothing to do with this problem. So the question is, do we have a formula for any of these things that is true regardless of this problem?
Centripetal acceleration is v squared over 3r.
Yeah, all right. So centripetal acceleration, v squared over r, or, do you have the other one there?
M times v squared over r.
That would be the centripetal force,
Yeah.
because that's mass times acceleration. There's another version of this.
R times W squared.
Anyone want to, you want to try that one again? All right, so first off, I understand what you're saying, and so the spirit is correct, but that's not a W.
I mean,
What is this?
it's an angular velocity.
Or speed, actually, but
Omega?
omega, yeah. It's omega squared r. Now, you would have written it down correctly and worked with it, just so long as you recognize that we're reserving the lowercase w for weight, and so I don't want people to think this is weight. This is not. It is angular speed. Now, in this particular case, we're going to use the v version of it. So, using substitution, this now becomes tension is equal to mass times v squared over r. R is given. I don't give you speed, though. How do we find speed? What is the formula for speed?
V equals d over t.
Say it again.
Is it v equals d over t?
D over T. Oh, D for distance?
I'm assuming yes.
Uh,
Or no?
yeah, delta X over delta D. It is distance over time. That'll give you average speed. Very average. Well, the only time I've given you is the time it takes to go around a circle once. So what is the distance it travels when it goes around a circle? You can give me the formula if you want.
You're talking
Oh,
about
wait,
like
hold
the
on.
formula for circumference?
Yeah.
Is it 2 pi r over t? No, that's not, oh, I